go ahead and get this down, and then we'll just kind of walk through it. It's just basically the overview so far of the first part of the SCR. So this is a silicon controlled rectifier. These are silicon controlled rectifier characteristics. Okay, so let's just go over this for a second. So if we look at the bottom right-hand side, you'll see down here, okay, you'll see that there's an anode and a cathode, right? And that should, just the anode and cathode by itself should be familiar. Everybody familiar with just a diode, correct?
Yeah.
Correct.
Okay.
Yes.
All right. So in this case right here, we have an optional way of actually triggering this gate. Okay, I'm triggering gate. Triggering the diode. And we call it the gate, okay, which is this component right here. So we have, basically we have 3 legs on this SCR. Normally, it just acts like a switch, okay? It's just an on-off switch. But there are 4 layers to this SCR. And what I want you to notice is that in this on the gate layer, what do we see right here?
A P.
A P, which is what? Represents what? So we have P and PN, right?
Positive?
There, thank you. There you go. I just want to make sure you guys see that. This is the
I just had a hunch.
Okay, so we're in a positive gate. Okay, this is the positive gate. So the gate is actually attached to the positive side, and this will make it makes sense once we look over here to the right. Okay, and we'll notice on step 6 right here. On step 6, we'll see that just like anything else, it's going to require that 0.7 volts to trigger that SCR. Does that make sense? And this is a positive 0.7 volts. Okay, it's a positive 0.7 volts. So it's just, basically it's just a type of diode, and the SCR contains another input called the gate, which we talked about. And it just provides an additional means of triggering, okay, for the on state. Now, the thing you really have to know about this is basically the information here, the knowing how to draw the schematic symbol, okay, of the SCR, and the information that you see on all 6 or all 7 of these steps. So this is just an overview of the information of the SCR. Okay, so let's go. Now we're gonna look at the equivalent transistor. How do we actually design an SCR using transistors? Because this is important, because you're gonna need to know how to do this for your lab, for the SCR lab, since we don't have SCRs on Multisim Live. So here we have our equivalent transistor. Okay, this is our equivalent transistor equivalent of the SCR. And you'll notice that we have 2 types of transistors. And what types are they?
PNP and NPN.
That's right. So we have PNP and NPN. So when you do your lab, you're going to have to configure it in this manner. Now your lab is pretty straightforward as well, because I've already drawn out the circuit for you. You're just going to have to build the circuit and determine at what point does the holding current drop off to where our LED doesn't light anymore. And that'll make sense when you see the lab. So the goal in the lab is to create and adjust certain potentiometers and so forth and triggers, which we're going to be using. You'll be using a switch, one of those little toggle switch in the Multisim Live, to turn it on and off. So on the spec sheet over here, if you were to look at the spec sheet, you would see several different parameters on that spec sheet. One is called the IH. All right, one is called the IH. That is the minimum feed-forward current, okay, required to maintain conduction. So that is our holding current. And the way this works is that once you throw that trigger, once you throw that switch, and you start getting conduction through the circuit, through your SCR, which basically is going to be through this, because this is what you're going to be building to represent the SCR. Once you get current flowing through there and you have enough current through there to light the LED, then you're going to open the switch in your lab. And then once you do that, you're going to see that the LED stays on. So the goal to begin with on your lab is to get enough current going through there to first trigger the gate, turn on the LED, and then throw the switch off. Basically, it looks like you're just opening the circuit, but in reality, you're not. You still have current flow through the LED and through the SCR, because the holding current, there's a minimum of holding current in order for this to continue conducting. And then once you drop below that minimum holding current, that's when the LED will go out. All right, now we have some other parameters on our spec sheet. And the first one right here is the second one is the ITSM, which is the non-repetitive surge current. What we don't want is, if you've ever had this experience before, sometimes you get surges at your house with your electricity, with your power and stuff. This is kind of similar to that, in that we want to know what is the limit. Okay, in other words, how much of a surge can we have without actually triggering this SCR into conduction? And that's what this ITSM represents. The VGD here, which is our gate non-triggered voltage, is the maximum gate voltage that can be applied without triggering the SCR into conduction. So whatever is on the spec sheet, that will be the rating for that one SCR, because there are a lot of different variables for SCRs. So if you were to purchase, or if you were designing something that needed to have an SCR, then it would be based on what kind of input you're going to have on that gate. So you want to make sure that whatever it is, if you don't want to be able to apply voltage to it without triggering it, okay, for some, random surge or something like that. Then we have our critical rise time, which is our dV divided by dt, which is our delta V divided by delta T. This is the maximum rate of increase in the analog to cathode voltage that the SCR can handle without false triggering occurring. And this is what we're going to do our calculations on here in just a second. So there is a certain time, okay? In other words, the amount of time it would take for current to flow through our anode to cathode and either conduct or not conduct. And we want to know what is the maximum rate of increase, all right, in that anode to cathode voltage. All right. Any questions on this? Are you guys still getting it down or what?
I got it down.
I'm still writing, but if they want to keep moving.
Okay, yeah, go ahead, Tess.
Another option is like screen grab it, if you can do that.
Is what?
Help. To screen grab it, like to do a screen grab, and then I do that a lot. That way I can go back and look at it. It will just save it automatically. You don't have to worry about not having it.
Right, yeah. Yep.
Screenshot, it works great. I think there's, I know on PC I can do it. I don't know about Mac though. Yeah.
Yeah, it can do it. I'm just not exactly familiar how to do it on the Mac. I'm sure it can.
Yeah, you're good. I'm good now.
Okay. All right. So here we have basically our graph of what happens during conduction. So if you notice here, here's some things. Let's first look at the parameters. So this is our negative voltage for anode to cathode. This is our positive side. This is our current, positive current for anode cathode, and this is our negative current for anode cathode. And this is our gate voltage, our gate triggering voltage. So first of all, it only works in forward conduction, in the forward conduction region, okay? It doesn't work in reverse bias. So in this case, we still need how much voltage here for this to start conducting? How much did we say?
0.7.
0.7, that's correct. So we need at least 0.7 before it kicks in to start conducting. Then once it starts conducting at this point right here and starts going up at like that, we are now in our forward conduction region, okay? So here's what I'm gonna try to explain. While we are in this region right here of conducting, this is simulating that you have on your lab, that you have closed the switch, and now you've allowed enough voltage, which is 0.7 volts, to bring about the breakover here and to start conducting in this region. So once it starts conducting, you're going to open the switch and basically creating an open circuit on that part. And then you're going to notice that we're going to maintain this forward conduction. Okay, so in other words, our LED is going to remain lit. What you're going to do is determine what is the holding current at this point, what is the value of that causes our LED to go out. So you'll start to decrease, okay, whether the pot or whatever it is that's on the lab, you'll start to decrease that to where your current starts going down, down, down. And then you're gonna, once it goes down and it gets to the point, you gotta keep an eye on your current. Once it gets down to a point to where it stops conducting and the LED turns off, that's gonna be the value you're gonna be looking for. Does that make sense? Does anybody have any questions on that?
Which way does that graph go? Does it go up and then loop back to the left where that straight line is, or does it go up on that straight line? Oh, I see. That's just a squiggly thing for the writing.
Yeah, that's just for this, right? That's just for this.
All right, I got it. Now we're on the same.
That's why I like to be able to explain this, so if you have questions, I can answer them right then. But do you understand what you're going to be attempting to do in your lab, right?
We're trying to get to measure when the what the current is when the LED turns off. I got that.
Which is going to be what you're trying to determine is what is this right here, this value of the holding current, right? So you'll keep adjusting your pot. You'll keep going down, down, down. It wants the LED at the same time. And, you know, good thing for us that Multisim Live actually shows the LED on and off. So you'll just keep moving it down and then watching the current on your meter. And as soon as that LED goes out, that'll be the current value that you'll be writing down on your lab.
Gotcha.
It's pretty straightforward and pretty simple. Unfortunately, we can't do a whole lot because they don't have SCRs, they don't have TRIAC, DIACs, and all that kind of good stuff. So that's why most of this is information.
For the lab, do you want us to use a push button or do you want us to use an actual switch?
No, I want you to use a switch for right now. It'll work, and Anthony, it will work with a push button because I've done that multiple times. I mean, if you want to use a push button, that's fine because it's pretty much instantaneous anyway when you apply the power.
Okay.
So
and there's nothing to find, hard to find about I never put a switch in on Multisim Live. No big deal to find it. Nothing special about that.
Nope, they're all on there, man. There's switches everywhere.
Okay.
Yep. So let me know when you guys have this. Oh, and by the way, I didn't tell you this. So this side over here, this leakage current, okay, that's if we started getting a negative voltage, okay, on our A to K. In other words, if we started getting a negative voltage on the gate, you go to a certain point and it's going to start leaking. Basically, it's draining, I should say, of current. And the value of this right here will be basically, it'll be in the spec sheet of how much negative voltage you could actually have before breakdown.
I guess you're just going to post the spec sheet with the lab.
No, you don't really need it because there's just so many different SCRs out there. Plus, you're not using an SCR anyway. You're using 2 transistors.
Okay.
I'm just letting you know where the information is if you ever.
Right, but we won't need that info for the lab. I got you.
Right. It's just information for you.
It's kind of hard to tell where the lines are going now. I kind of see.
Which lines, Thomas?
I see the main line where it's just a straight line, and then it goes up a bit. And
yeah. So what happens is that here's our line, right? Here's our primary line. Do you see this?
yeah, I see it.
Okay.
Wait, what?
That's our primary line.
Yeah.
At this point right here in the middle, that's where the gate trigger is.
Mm-hmm. Okay, I see it now. Thanks.
Okay, so let's do some calculations and look at a formula real quick. Okay, so in our first example, so our formula basically is the dV over dt, our delta voltage divided by our delta time. So the change, we have the change in time, which is this right here, okay, which is the rise time of the increase in VAK. In other words, voltage across from anode to cathode. On this one right here, our change in voltage is the amount of change in that voltage from anode to cathode. So we have a rise time, so we're dealing with time, and we're also dealing with voltage itself. All right. So in our first example, in this case, we have a 2N 682 SCR being used where there is a 2 nanosecond rise time noise, okay, signal occurring randomly. So this is a random noise, a random amount of current or voltage going through our circuit with a critical rating of 50 volts per microsecond. The amplitude that will cause false triggering is found as this right here. So we have our delta, our change in voltage, divided by our change in time, times our change in time, which is our 2 nanoseconds. This is where we're having that problem. We want to know, okay, we want to know what is the voltage or the amount of voltage here that will cause false triggering. What is the amplitude of that voltage that will cause a false trigger based on the SCR being used is 2 nanosecond rise time. The noise signal occurs randomly. I mean, this one's almost done for you anyway, so, but just make sure you have the calculation down correctly. And then let me know what value you come up with for A.
So we're just doing the 50 volts.
Divided by per microsecond.
Right. So just do that times 2 microseconds.
Times
and then
2 nanoseconds. That's
nanoseconds, I mean, and then do 50 divided by 10.
No. I just broke this down right. Oh, wait, hold on. I broke this down right here to be this. So.
Okay. Yeah, so it's same. Okay.
It's just 50 divided by 1 microsecond is what it is.
Gotcha.
And then let me know what the voltage is.
I got 10.
10 volts?
Yeah.
Nope.
Huh.
Try it again, Thomas.
So 50 divided by 1 microsecond.
Times 2 nanoseconds.
Mm-hmm.
A nanosecond is to what power? Negative what?
Ah, anybody want to tell Matt what that is?
-9.
That's
All
what,
right,
that's what I thought.
Anthony.
That's what I got. I have it bleeping in the thing here, but so I got 100 milli.
Perfect. So
Same
that-
thing.
I was doing 200 nanoseconds. That's why I got
okay.
10.
So 100 millivolts. Okay, so the amplitude here is 100 millivolts that will cause false triggering. So if we had, this is what happens now. If we had, by some freak chance, a 100 millivolt across our SCR, then it would trigger into conduction, and this would be false triggering. And that's what we're trying to figure out. What amplitude or what voltage would cause false triggering in this condition? All right, so let's do this one more here. Let's do B. You have another SCR, it's a C35D, and the critical rise rating on this one is 25 volts per microsecond, and the noise signal rise time is 100, what is that?
Pica or something like that? Negative 12.
Picoseconds.
Say it again, Anthony.
Picoseconds.
Yeah, negative 12,
Picoseconds.
right? Negative 12, right?
That's correct. So what would be my false triggering voltage?
$500.
Nope.
What did I do wrong? 25 divided by 100.
2.5 millivolts.
What? There's 25 volts
Oh,
per microsecond, and then you got 100 picoseconds.
What did I type in?
2.5 millivolts.
All right.
Oh, you switched it to micro, not net.
Hey, I said that.
Okay.
2.5 millivolts. I thought that was incorrect.
Millivolts. So basically what happened is we changed our critical rise time, right? We changed this rise time from this is 100 picoseconds here, and on this one it was 2 nanoseconds. And then on this one right here, we have 25 volts per microsecond, and up here we had 50 volts per microsecond. So that's all we changed, was those two values. That's it. All right, any questions on this? You will need to know how to do this. I'm
No.
tell you right now. Okay, so the rest of this stuff is pretty much information, and then I might have something I can show you here, but anyway. Okay, so now we're looking at DIACs. That was SCRs. Now these are the information characteristics of a DIAC. All right, the DIAC can have a latch current in either direction. Remember, the SCR only conducted on this side right here for the SCR, but with a DIAC, we can now do conduction in both directions. That's why we refer to this as a two-terminal bidirectional device. In this case, it has no gate. And you're thinking, well, how on earth are we going to be able to, what kind of application could we use that would conduct in both directions? Does anybody know any kind of signal that would conduct in two different directions?
AC, right?
Right, AC, right? Because right here, full AC. So AC, we have the positive side and the negative side, don't we?
Yep.
So now we can have conduction in both direction, on the positive peak and on the negative peak.
So that's how you go from DC to AC with a rectifier.
No, this is not used for that. Okay, these are used to trigger full wave AC applications, whatever requires an AC signal. So in other words, we can run different devices that run on AC, is what this is doing, that require power.
That's what I was saying. Like you could like a motor.
Yes, exactly, like a motor.
Because they have them inside of the lifts that take you down the side of a building.
Yep, exactly.
They have them in plumbing motors, pumps.
Yep. Now you're getting it. That's it. Oop. So go ahead and get all this information down. That's all this is, just information. So you'll need to know all this.
What is the difference between that rectifier and like a rectifier you would use if you had like a solar panel and a battery bank?
Well, that's an inverter.
Oh, inverter, yeah, you're right. We're going the other way. Okay.
Yeah, we got inverters and we got converters.
Yeah, the converter, that's like what's on your wall plug that takes it from the wall to DC, right?
DC.
Like our power supply.
Yeah, that's a converter from AC to DC.
Yep.
So have you ever seen those inverters that you plug into a cigarette lighter in the car?
Yeah. Oh yeah,
I
have.
That turns it into AC.
Right. Yep. Yeah, you can get them that'll do like 2,000 watts. You mount it, you hook it right to the battery and mount it under the hood.
Oh yeah, they work good.
I mean, that's like having a small generator with you everywhere you drive your car. That's amazing.
Yeah, I know. The only thing, you got to keep the car running though. Unless if you turn the car off, the battery's going to die pretty quick.
Yep, especially at 2,000 watt.
Yep.
Little cigarette ones are usually like 300 watts. They're pretty small. But they will run your laptop.
Oh, absolutely.
I'm ready whenever.
Oh, okay. Tess is good. Thomas?
I did too.
Yep, I got it.
Got it.
All right. Okay, so now that was the DIAC. Now the TRIAC. Okay, this is the TRIAC. And if you look at this, we're going to see that we have two SCRs in parallel to create a TRIAC. TRIAC acts like, basically, like I just said, two SCRs in parallel, equivalent to a two-latch. Okay. It is a 3-terminal device, similar to the SCR, because this also has a gate for triggering. Just like the DIAC, current flows in both directions. Current flows in both directions. So we have conduction on the positive side and conduction down on the negative side. Okay, and these are primarily used to control power AC loads like motors, heating systems, and so forth, because the way they're designed is they can handle higher currents. But this will be all the information you need for your test next week. So make sure you review any PowerPoints, if we have PowerPoints, lectures, or whatever.
Like the JFAT and all that?
Yes.
Mo whatever.
Yep, starting with JFATs and all that stuff, yes. But like I say, if you took good notes and everything, this should be a walk in the park for this next test.
Good.
And also, make sure you guys check your D2L, okay? I've told you that before, because for this week, You got homework and you have your second quiz online. I mean, it gives you the information on where to go for it.
Do we have homework for ELC 2252 or just the lab?
Just the lab for that one. So, but for this class, you have your second quiz and you have homework 3.
And the quiz, is that due by a certain time or?
Yeah, it's due by Sunday.
Okay. Well,
It's
I meant
just,
like it's not like a test where we have to be there at like 3 o'clock till 5 o'clock.
No,
Yeah.
it's just like it's a 1, I think it's a 1 or 2 question. I forget what it is. Anyway, it's a question out of your book. All right. Once you get all this down, that is it for today.